Hello, students. This is part two of the February 6, 2025 class. So why do stars rise and set? And that has to do with our motion of our planet rotating around its own axis, right? So sometimes, from our perspectives, is it if we on Earth are standing still and all the stars are just moving around us, right? That is one perspective, but the reality is it is our planet that is moving around. I like this little animation over here because you really have more of the sensations. Our planet is moving around. And so what happens is we have, as we look north, right? So we look towards the north, and you can, that's a question I would ask you later, but I'm going to highlight that. That little star track is actually our star Polaris, our star that we call our North Star. But you can see how Polaris is not quite at the center of that circle, right? That there is no real center to that circle. The Polaris is a little bit offset. It makes a little arc around the center of that circle. So we know that Polaris, what we call our North Star, is actually about 1 degree away from the position that is actually the North Celestial Pole, the North Celestial axis of rotation of our planet. And 14,000 years from now, this is going to shift so much that what we will call our North Pole star is going to be a star called Vega. The same Vega I mentioned in part one. Vega in the constellation of Lyra, it's a star that's very bright in the summer. It will be in our planetarium test. You'll see that when we go in the planetarium. So, how was this picture here taken? You're facing north, so you will see this. It was a long exposure, right? They were facing north and they were taking this exposure over hours so that you can see the star trails over hours, right? And so this was taken somewhere where you can see the North Celestial Pole, right? Or you can see Polaris. So if you can see Polaris in the North Celestial Pole, it means you are above the equator. So if we were standing on the equator of our planet, Polaris, it would show just at the horizon always, and it would not be above that horizon. So because this picture, we can see some star trails here that of some stars that never rise and never set. They're circumpolar, they stay above the horizon, they never go down. Because we can see some circumpolar, well, here stars, it means that this person here taking this picture is in the north hemisphere and some degrees. I would say this looks like about 10 degrees or so above the the equator. Right? What happens if we are in the North Pole? In the North Pole, this little circle here, what is our North Celestial Pole, would be at the zenith on top of our head, would be on top of our head. If we were standing on the North Pole, we would see Polaris on top of our head, approximately within 1 degree, right? And we would see all the Star Treks always doing circles around us. It would never set, never rise, right? So we can already say that this picture was not taken at the equator. This picture was not taken at the North Pole, and it was somewhere in the northern hemisphere. But maybe let's estimate a few degrees. I don't know. I'm saying 10. You don't need to be that precise here. We need more information, but a few degrees above the horizon. Okay. So, except for the circumpolar constellations or stars that you can see that never rise and set depending on your latitude, all the other stars in the sky will rise in the east and set in the west. Will rise in the east and set in the west, right? So that's what we see the stars doing. And why are the stars doing that? Because in reality, it's Earth that is rotating. And then Earth is then rotating. Well, if the stars rise in the east and set in the west, the Earth is rotating, well, in a west to east manner, opposite to that. Okay, so let's see another picture here. We already talked a little bit now before I move on, again, referring to this picture here, right? So Earth here's here in the middle. This is our equator in black here in the middle. Our planet rotates. If you always look from the top above our planet from the north celestial pole. So if you, and that's normally how all the pictures of the solar system, all the pictures of how planets rotate, they are always going to be be shown from a perspective, most of the time, from above the North Celestial Pole. So you're looking from the North Celestial Pole down towards the Earth, towards the whole solar system. And our solar system was made in such a way that disk that formed all the planets and the sun and all, that disk was spinning when you look from above, from the North Celestial Pole, it looks like it's spinning counterclockwise. And so all the planets that we'll see are orbiting around the sun in a counterclockwise manner, and that has to do with the way the whole cloud that formed our solar system was spinning. It could have been set up to spin clockwise for 5 billion years ago, but somehow it was set up from the get-go to be spinning counterclockwise. And all the planets are still going, and the sun is revolving around its own axis, and so all counterclockwise. Well, not only all the planets are moving around the sun counterclockwise, but also most planets, now here there are some exceptions, so watch out. Eventually you're going to need to know the exceptions, but most planets also around their own axis are also rotating around their own axis, as you can see here in this picture, also counterclockwise. So not only they're revolving around the sun counterclockwise, but also around their own axis counterclockwise. So here you see this picture here on Earth, that's the equator. This thing here on the outskirt, the outside, this blue sphere on the outside is that imaginary celestial sphere, right? Where we project our constellations. So it's a very good model for us. It's imaginary, it doesn't really exist, but it allows us to map the sky, right? So we always talk about the celestial sphere, the north celestial pole. So if you extend this, you're eventually going to get to very close to Polaris, right? So the north celestial pole is aligned with the pole of orbit rotation of our planet. And I want to highlight as we are here in this picture that the equator of our planet is actually also aligned with the what we see here, the celestial equator. So the celestial equator and our Earth's equator, they are all aligned with each other. So it's as if we extended Earth's equator all the way far, right? That imaginary celestial sphere, and that's the so-called celestial equator as well. It will be important moving on. All right, so very important for us to again understand this perspective that in general, most pictures of how planets are spinning around their own axis, how planets are moving around the sun, they will be pictures that will show the planets from that north top view. So we are looking at our planet to see this is the North Pole, right, of our planet. This is the North Pole. This is Greenland, right? Here you have Canada, you have Alaska, and here is what? The west coast of US, right? So the west coast. And here what you have, the east coast of US, right? So therefore this side is east and this side is west of our planet, right? So our planet, when we look from this point of view from above the North Pole, is spinning in what we call a counterclockwise manner, right? This is opposite to the direction of the clock. So this is counterclockwise, opposite to the direction of the clock. It is okay also to say that is then our planet, right, is spinning from west toward the east, right? So here's the west coast, and our planet then is spinning towards the east, right? So as our planet is spinning from west towards the east, when we look from above the North Pole, right? From above the North Celestial Pole, then even zooming out more than just Earth's North Pole, the North Celestial Pole, zooming out even further, we see our planets moving counterclockwise. So two complementary ways to describe how our planet is moving. Having said that, many times we'll prefer this counterclockwise, always seeing from the perspective above the North Pole. If you were if you were from a different perspective, like below the South Pole, you could not say counterclockwise anymore. So watch out. You always also have to make sure what is your definition here from above the North Pole, as it will be by far most all the time. So here there's a little thought question, which was kind of answered already, but let's see. What is the arrow pointing to right there? Okay. So there are three options. Is it pointing at the zenith? Zenith is that point, as we've learned, all above your head. This is the horizon of the picture right here is the horizon of the picture. So definitely the zenith, I don't know, maybe this picture makes it to, it will be way up. So that's definitely not the zenith, right? Is it a celestial equator? So as you've seen in the picture below, a celestial equator lines up with Earth's equator, right? And if you were at the equator, we argued that you would not be able to see any circumpolar stars because the North Star would be down here. So there would be all stars would rise and set and there would be no star above the horizon all the times of the year, right? So if you were at the equator and therefore able to see in your horizon the celestial equator, this point here would be on the ground on the horizon. So it doesn't make sense to be the celestial equator. So the right answer is the North Celestial Pole. And we know actually this point here in the middle really is the North Celestial Pole. The little arc there is Polaris, which is 1 degree from our North Celestial Pole. But the North Celestial Pole is definitely the best answer for this question. Okay. So moving on, emphasizing this, that stars near the North Celestial Pole, likewise, if you're living the Southern Hemisphere, stars close to the South Celestial Pole, they are called circumpolar stars. They never set, they never rise, they are there on your sky all the times of the year. So you look at night, you are sure you're always going to see those stars and those constellations, the circumpolar ones, whether you're in the north or in the southern hemisphere. You need to be right a few degrees above the equator or below the equator, and you're always going to have some circumpolar stars and some circumpolar constellations. Those that never rise, never set are always there in your night sky, no matter what. Now, the rest of the constellations that are not circumpolar, they will always, to our perspective, rise in the east and set in the west in our night sky, right? But so the sky does change as the year goes by, as time goes by. There are many constellations that will be different. Rise in the east, set in the west, and they will be different. The circumpolar, however, are once given your latitude, you're always going to have those specific circumpolar constellations and stars that will always be there in the sky for you. All right. So it's nice for us to get acquainted and understand these little pictures here, right? So this could be a picture of someone living at, let's say, approximately 40 degrees latitude, right? Like us, Long Island here, in New York, etc. So here you are on Earth. So that's the little black picture right there. It's you standing at a latitude, I don't know, north. So I'm drawing here with the red line the horizon for you, right? So you see here marked also in the picture your local horizon. So your horizon is tilted like this, right? And the North Celestial Pole then for you, and therefore moving on here, keep going Polaris, right? Because very close to Polaris would always be what? A few degrees above the horizon for you, right? That's your horizon line, and you're a few degrees above the horizon. That's where Polaris would be for you, right? The celestial equator would be somewhere crossing, somewhere high at a different location there for you, higher above the horizon there for you. So why do constellations we see depend on latitude and time of the year? Well, maybe this slide should start by saying the constellations you see depend on latitude and time of the year. Right? And why is that so? Well, uh, latitude is your location, how far north of the equator or south of the equator you are in our planet. So you can imagine that if you are north of the equator, you're just going to see a different part of the universe. And if you're south of the equator, you're just going to be able to visualize another bottom part of the universe. In fact, only people in the southern hemisphere can see, for instance, the Magellanic Clouds, the small and the large Magellanic Clouds, which are two very nearby dwarf galaxies falling into our own galaxy, and they are little clouds in the sky that can be seen with naked eye, but only people in the southern hemisphere see them because these two little galaxies are located sort of south of closer to the south celestial pole for us. So you will see different parts of the universe, whether you're in the south or in the northern hemisphere of our planet. Hopefully that makes sense, and we emphasize that with a few more slides. And we already, I think, discussed this, that the time of the year will also change what parts of the sky we're seeing as we're moving around the sun, right? The sun then is going to be sort of blocking during the day certain stars, right? We don't see stars during the day because the sun just uh, uh, overcomes with all its luminosity any star will. The light gets scattered in our atmosphere. We don't see the stars during the day. But then at night, then, as we look opposite to the sun and we're moving around the sun, we'll be scanning different sections of the universe. So it makes sense that as constellations change, as time of the year changes. Again, the only exceptions are circumpolar constellations, those are always there. But all the others that are not circumpolar will be changing with the time of the year, right? Okay, um, so um, there are always two coordinates we need to define a point in space, right? Like in mathematics, you needed x and y to find a point in a two-dimensional space, right? So on our planet, the coordinates we use to find things in our planet are latitude and longitude, right? To be very precise. And what is the latitude then? Is how far above the equator? The equator has a latitude by definition equal to 0 degrees. What is the latitude of the North Pole? Is plus 90 degrees. What is the latitude of the South Pole, right? Here it's not even showing, minus 90 degrees. So in between, so latitude is going to tell us how far up we are. So from 0 to plus 90 north, and will tell us how far down we are on our planet from 0 degrees to minus 90. Now we are so used to seeing our planet like the north is up and the south is down. There's no up or down, sorry, in the whole universe, remember, right? It's just our convention, right? But there we go. So therefore, latitude will be a especially important coordinate for us to understand the sky. We already saw from the previous slide that the constellations, the stars we see, will really depend on the latitude, where we are in our planet, right? Now, another coordinate necessary to define a point in our planet is longitude. Now, longitude is not going to be important to understand the night sky, to understand what part of the universe we're seeing. Longitude, basically, right, is longitude. By definition, it tells us our position east or west, right, of the prime meridian. We define the prime meridian here to be longitude equal to 0, to be a meridian that passes by Greenwich, very close to London in England. That's a definition, an arbitrary definition, right? The longitude tells us time zones in our planet, right? And basically, no matter where you are in our planet, you will see the same type of stars and constellations. It's just that it's going to be at different times of the day or the night, right? So it's different because you are living in different time zones, but you have the same view of the same patch of the universe. It's just that someone, say in Europe, will see that patch of the universe earlier, and several hours later, someone in the United States will see that same patch of the universe. So longitude is not important for us to understand if we see different patches of the universe or not, because it will be the same for all of us. It's just a different, shifted by time zones. All right, what are the latitude and longitude for us here, even as Selden and Ammerman, they are our campus here, right? We are at around 41, let's say 41 degrees. Okay, so we can write degrees 40.8, la la la, and we can write degrees as being as decimal places, so 40.8, or we can write them as 40 degrees, and now this point 8, I will multiply them by 60 to get a value in minutes, our arc minutes, as we learned before. So 0.80 translates out of 60 as 50 arc minutes. And then there's more broken decimals, and I can even translate that to arc seconds. So we can write latitude also as a 40.8, etc. decimal place, or with arc minutes and arc seconds. Okay. And sometimes we drop the word arc, and just say minutes and seconds, right? What is our longitude, by the way? Minus 73 degrees, or 73 degrees west if we drop the minus. Again, longitude is not going to what we're going to focus on. We will need more latitude. All right, so in the northern hemisphere, Polaris is the nearest is the star nearest to the north celestial pole. In the southern hemisphere, there is no such a star. So we just saw the Polaris is about 1 degree away from the what we call NCP, the North Celestial Pole, about a degree. So Polaris is really close to our North Celestial Pole. And Polaris's right part is one of the brightest stars in the constellation of, as we'll see, Ursa Minor. And another very big and bright constellation, or part of it called an asterism of that constellation, is going to be the Big Dipper next to it. And we're going to see more of that in the planetarium. If you follow these two stars called the pointer stars of the Big Dipper, this is called Dubhe, this is called Merak. These are going to be in your planetary test. We'll go to the planetarium and review that. If you draw a line between those, they are on the ladle part of the asterism of the Big Dipper, right? It looks like a frying pan with a handle and the ladle or the frying pan. If you draw a straight line between Dubhe and Merak and extend that a few times, you will point to Polaris. Right? Polaris, furthermore, in the planetary is that star that anyway is going to be right above the letter N for the north. In the cardinal points will always be shown to you in the planetarium to help you guide your eyes. So the Big Dipper, very bright stars in part and asterism of the larger constellation Ursa Major, they can guide you also to the north Polaris, or just look at the letter N, go up, and the brightest thing you see above the letter N will be Polaris. Now, Polaris is part of the Ursa Minor constellation, right? And its asterism, the Little Dipper. So it is easier in the northern hemisphere to find what is this north celestial pole where Earth is spinning around. Now, in the southern hemisphere, unfortunately, there's no bright star where would be the south celestial pole, the south celestial pole. So if you live in the southern hemisphere, the brightest thing you always look as a reference is called the Southern Cross, is that constellation of the Southern Cross. And you would have to look at that for quite a few hours. And then whatever the longest axis of the Southern Cross intersect, that is your southern celestial pole. In school, if you grow in the Southern Hemisphere, you learn, they say once you see the Southern Cross, just extend its longer length about 4 times, and there you go. That's your South Celestial Pole. Okay. And if you then draw a line straight down, that is south projected on the horizon. All right. You don't need to be scared about all the angles and what is showing here, but from here, the point, what we want to make, the point we want to make here is this, that the altitude of Polaris in our sky is equal to your latitude, okay? So this is very important point we want to make, and this will be in tests and etc. So this is what this drawing is showing. You, with knowledge of trigonometry, can actually demonstrate that. We are not going to ask you to demonstrate in Astronomy 101, but I'm showing you this. Say here there is you are here standing at 50 degrees of latitude above our equator. This is Earth's equator, okay? And so this is north, this is south, pole of Earth, and you're here standing, and that's your horizon. This whole thing here is your horizon, right? On the Earth. And at this latitude of 50 degrees. Where is Polaris? Polaris is up here, right? So if you, now Polaris is always straight up parallel to what is the north, right? So you go up, you find Polaris. So this is where Polaris is. And using trigonometry and complementary angles, I'm not going to go in detail here for you, but basically Polaris, just like you are at 50 degrees of latitude here, the height from your horizon, if you look at your horizon and use like your hand, right, to measure, this is 20 degrees, another 20 degrees, another 10 degrees. This is the closed fist would be 10 degrees, right? 20 plus 20 plus 10. You see that Polaris for this person here will be 50 degrees. That's exactly the angle it does above that person's horizon, okay? So that's what we're saying here. The altitude of Polaris is equal to your latitude. If you're ever dropped in a desert island, the first thing you would, hopefully in the northern hemisphere because it's easier, if you need to find your bearings, you find where you are, one of the first things you would search for circumpolar constellations and Polaris, right? Because Polaris is going to tell you what's your latitude. So if you see Polaris at the horizon, you are at the equator. If you, and Polaris is always going to be there, it's not going to change, it's not going to move, right? So even as the sky spins and most of the stars rise and set, Polaris is always going to be in the same position. So if Polaris, however, you measure with your hand is say 40 degrees above your horizon, then that's your latitude. And indeed, you're going to see something like Ohio, you're say you're somewhere in Ohio or somewhere. Here in New York State, right, we are 41 degrees. Okay. So when we go inside our planetarium, for instance, or if you when you go observing at night, hopefully we will have an opportunity that you will see that using your hand from the horizon, two open hands will get you to the height of Polaris in the sky. If you see Polaris right on top of your head, it means you are, so it's 90 degrees above the horizon. You are on the pole. You are on the North Pole, right? All right, so important altitude of Polaris is equal to your latitude. Altitude is measured in degrees. Latitude is measured in degrees. It all makes sense. So the North Star Polaris is 50 degrees above your horizon. So say you saw Polaris, you say you use your hand and so it's 50 degrees above your horizon. So where are you, right? Hopefully this question is easy to answer as we already dealt with this, right? You are at latitude 50 degrees north. If you see Polaris, it has to be north. And we just were highlighting how the altitude of Polaris is equal to your latitude. So don't worry about the word longitude, worry about the word latitude, right? Okay. All right. Our planet is the axis of rotation of our planet is wobbling in every 26,000 years. So we said that Polaris is about 1 degree away from the North Celestial Pole. And that distance over thousands of years in degrees will increase eventually in 14,000 years from now. Our North Star will be that star Vega in the constellation Lyra that we see more in the summer. And why is that? Because our planet behaves very much like a top. What you're seeing here is like a top. What happens when you spin a top? When you set a top to spin, very likely the top will start wobbling. While it's spinning, it is also wobbling, right? While it's spinning, it is also wobbling. This wobble is called precession. Precession of the axis of rotation of the Earth. That happens. Why that happens with the top? Why that happens with the Earth? Well, somehow, maybe there was a collision that tilted it, and right, and it keeps spinning, conserving something called angular momentum. But it got tilted because of a collision or something like that. So that's what would happen with our planet. When you do that with the top, maybe somehow the way you started spinning it already had a little more of a torque or a force in one direction or the other. Or it's just that even when you make any object, even our planet Earth, it's not, the mass is not perfectly distributed in all directions. There's going to be one little region that's a little bit heavier than the other, and then it tilts more towards that and it starts wobbling. So our planet here, its axis of rotation wobbles, okay? So it precesses, and it precesses every, well, we'll see in the next slide, every 26,000 years. The current angle that it makes with the plane of the ecliptic. So here is the plane of the ecliptic as the Earth is going around the sun, okay, the ecliptic. And our planet is tilted by, in respect to that plane of the ecliptic, by this angle here of 23. Actually, nowadays, more precisely, is 0.4 degrees. That would be the axis of rotation of our planet, okay? And so you may see 23.5, 23.4 in homework or in a slide. It's okay. We're never going to bug you much with that precision, okay? Even the value of that tilt changes over larger time scales. I think it's 40,000 years for that, from like 21 to 25 degrees. Even that amount of tilt changes. Not only the tilt wobbles, but even the amount of the tilt also fluctuates at a longer time scale. So in the precession period, okay, the precession period is about 26,000 years. It means that right now, say Polaris is a North Pole star. Within 26,000 years, Polaris will be again a North Pole star. But halfway through, which I don't know, 13,000 years from now, it will be now the star Vega, okay? Or Vega. So it's good to know about the precession of Earth's axis. So we talked about now the fact that as we are moving around the sun, the constellations we'll see, the parts of the sky we'll see will be different as throughout the years we're moving around the sun. Another way of saying that is that the constellations change with the seasons, right? As we're moving towards the sun, there are different seasons in our planet with different seasons, different constellations. So let's talk about seasons then. True or false? Earth is closer to the sun in the summer and farther from the sun in the winter. So before you answer, think about this. When it is summer in the US, well, right now it's winter in the US. What's happening in Australia right now? It is summer in Australia, right? And vice versa, when it's summer in the US, right? It is winter in Australia. And you must have heard of that, or same, or if you prefer the reference of South America or Africa, right? So the North Pole of the Earth has a different season than the North Hemisphere of the Earth has a different season, opposite season to the Southern Hemisphere of the Earth. So we live in a planet, and that happens with most planets that have a tilt. Most planets that have a tilt will have opposite seasons in the North and the South Hemisphere. Not all planets have tilts, though. So if a planet has a tilt, it will have opposite seasons in the North and the Southern Hemisphere. So let's go back to our question here. So I'm already giving you hints of what's the answer. So let's go back to our question here. If the Earth was really a lot closer to the sun, and that's why it's summer, it would be summer for all of us, right? North and Southern Hemisphere, because it's just too hot. It's as if the closeness to the sun is what is dictating the season, it would be hot equally for all of us, North and South Hemisphere. So that sentence is wrong. The seasons, right? The real reasons for the season involves the axis, the tilt of Earth's axis, and not the proximity of the sun. So our all the planets when they're orbiting another star, and this is even beyond our solar system, they follow elliptical orbits, oval orbits around their central star. And In the case of the Earth, this oval orbit is almost circular. Is its ellipticity? We say its eccentricity. How much it is stretched? There's almost no stretch. It's almost like a circle. So for the Earth specifically, there is not much difference in distance in when the Earth is at its closest point to the Sun in its orbit and when it's further. So for the Earth, it's really negligible that difference of distance to the Sun. And so for the Earth, the what dictates its seasons is really the tilt of our planet. Okay. Now, we're going to talk about Mars. Well, actually, we are Astronomy 102, so we're not going to talk about Mars so much, but Mars has a more eccentric, meaning more oval orbit stretched around the sun. Sometimes Mars will be substantially closer to the sun than other times. So Mars, however, has a tilt like the Earth. So Mars will also have opposite seasons in the north and southern hemisphere. However, when Mars is closer to the sun, it means its southern hemisphere, which is summer, is going to be a scorchingly hot summer, and the northern hemisphere, which is its Martian winter, is going to be a very mild winter. So for different planets, you got to take into account actually back again, think sometimes some planets will be significantly closer, and that will affect at least the severity of their seasons, right? Uh, but if they have a tilt, if a planet has a tilt, then north and southern hemisphere of of whatever's the planet will always have opposite seasons. For Earth, it's just the tilt of the Earth that is the factor that causes the seasons. So here's the Earth moving around the sun. As we said, Earth makes an angle of about 23.4 degrees with the plane of the ecliptic, right? So this would be perpendicular to the plane of the ecliptic, makes 90 degrees. The ecliptic here is what is in red here, as Earth is moving around the sun. And so our planet is tilted by this 23.4 degrees. So what happens here, let's talk about referring here, this is all referring to reference here is always the north hemisphere, okay? Hemisphere, I'm going to put just like that. So referring to the northern hemisphere, so this is a southern solstice. So what does that mean? What is um okay, should have started? Well, southern solstice. So that when it's solstice in the south, so this is going to be when it's winter in North America. Okay, winter in the northern hemisphere. I want to refer to the northern hemisphere for you. So winter in the northern hemisphere, that's what? That's December, let's say December 21st, right? That's the southern solstice. That's when it is summer in the south, but it is winter in the north. So it is winter here in the north, right? And it is summer here in the south, right? So what is happening? I told you the reason for seasons is the tilt. So what is going on here in this drawing? The first one we're going to say, how does the tilt really explain the seasons, right? And some students sometimes look at this. Of course, this is really out of scale. The distance between Earth and Sun is enormous. But when students see this type of picture, they say, ah, look at that, it's tilted this way. So it looks like the southern hemisphere is closer to the sun than the northern hemisphere. It has nothing to do that. They are equally distant. The distance between Earth and Sun is so large that the little tilt is not substantially bringing the southern hemisphere closer to the sun. That's not the reason. It's just that the northern hemisphere will really get the more direct sunlight, right? What is the hottest time of the day? When the sun is really high up. So when the rays of light are almost direct above your head, that's the hottest time of the day. When the rays of light are lower in the horizon, when they get to you at a very large, shallow angle, it just won't warm you up as much. So what the effect here is whether the rays of light are the most direct, and they will be the most direct here Sorry, should have drawn the opposite thing. So, hold on a second. Professor made a mistake here. So the rays of light will be the most direct for people in the southern hemisphere here. Actually, it will be the most direct. And for people in the northern hemisphere, right, the rays of light, say if you're standing here in the northern hemisphere, you're going to see the rays of light like coming to you kind of low. But if you're standing here in the southern hemisphere, right, you're going to see the rays of light coming really, right, high up. So it is summer. The rays of light are incident more directly towards you. Whereas here is winter because the rays of light are at a shallow angle, are more indirect towards you, so you don't get as much warmth. What happens at the equinox? The word equinox, equinox. This is the spring equinox. This is the fall equinox. So what is going on here? The That's when the tilt of the Earth is not playing a role and is not, say, making one of the hemisphere receives more direct sunlight than the other. So both hemispheres get the same amount of direct sunlight. And back again when it is summer for us here in the Northern Hemisphere. So for summer for us here in the Northern Hemisphere, you are receiving most of the direct sunlight. Where the Southern Hemisphere, because it's more tilted away from the sun, you will get the indirect sunlight. So it will be winter there. Okay, so this is June 21st. June 21st, right? All right, moving on. So, few words you must know what is solstice and what is equinox, right? And then we have a summer solstice, winter solstice, right? And we have to define those. Those are summer solstice for the northern hemisphere, for the southern hemisphere. You do have to ask yourself, are you talking about summer or for the northern or southern hemisphere, right? But solstices in general, if you, right, what are they? The when one of the hemispheres is going to be more tilted towards or away from the sun. And that is our June 21st or our December 21st, right? And equinox, we have the spring or vernal equinox, the fall or autumnal equinox, right? So the equinoxes are the times where the tilt of the Earth is really not influencing as it's orbiting around the Earth, orbiting around the sun. The tilt is not directed towards or away from the sun. The tilt then is neutral. It's equinox, meaning both hemispheres getting the same amount of direct sunlight from the sun. But during the solstices, the tilt of the Earth is really tilted away or towards the sun, making one of the hemispheres be away or towards the sun. Therefore, one of the hemispheres receiving more or less sunlight. And that's the reason for the seasons. That's the reason one hemisphere will be hotter or colder. So here we have the path of the sun during the solstice. So when it is summer solstice, the sun will always reach a higher altitude in the sky above the horizon at noon. When it is winter solstice, the sun will be reaching the lowest altitude in the sky at noon. And equinox is somewhere in between, right? And the equinox is the only time the two fall and spring equinox, right? The equinoxes, they are September 21st and they are March 21st, around those dates, right? They are the only times where the sun perfectly rises in the west and perfectly rises in the east and sets in the west. All the other times of the year, the sun will be shifting setting north of west or setting south of west, right? This is for someone in the northern hemisphere. Most of our textbooks and all will refer to things happening in the northern hemisphere. So this would be exactly the design for the northern hemisphere, summer solstice for the northern hemisphere. So the sun is more towards the north of west, setting towards the north of west when it's summer. And the sun is setting more south of west when it's winter. Likewise, it rises south of east and when it's winter, and it rises north of east when it is summer. So here is sunset time. So I'm going to tell you straight away, this is west, this is sunset, right? So this is so if this is west, and so the sun is higher up in the sky when it's summer and lower in the sky when it's winter. This is a montage, but it's telling you that if the sun, you can see clearly see, reaches higher height altitudes in the sky, so that must be summer. Now, Boy Scout, Girl Scout technique, right? If this is west, right? If you're facing, say this is west, then think about it. To your right must be north, and to your left must be south. These type of things of finding the coordinates, where's north, south, east, west, this will be important eventually in a test, etc. May give you a picture, may tell you something about it. Oh, this is sunset or the sunrise. Where is east? Where is north? Where's south? And things like that. So make sure you know how to position yourself and find the cardinal points. All right. I have stopped here for several of the other classes as well, so I'll stop here for you. When you come back next week, when we are in phase again on February 13, because we don't have class on February 11, we'll go over a little bit more about the seasons and which will be will be a big deal in your lab 3. Okay. And then we wrap it up and start talking about light. All right, guys, so have a good one. Thank you for your attention, and hopefully you watch both parts. Take care.